Hello friends, welcome to my channel Physics with Rakshi. In the present video, we will see 8th chapter of the book Look Quantum Gravity for Everyone, authored by Rodolfo Gambini and Jorge, Pullin. Name of 8th chapter is Possible Observable Consequences, particularly quantum gravity. Can we measure look quantum gravity using current technological regime or not, using current experiment or not? That we will see in this lecture. Let us start. We know that unit of quantum gravity is Planck units, in which we consider Planck energy, which is of the order of 10 raised to 28 electron volt. Planck length, which is of the order of 10 raised to minus 35 meter. Planck time, which is of the order of 10 raised to minus 44 second. These all magnitude will require in the present video. Let us see. In previous videos, we saw that in cosmic microwave background radiation, there are some imprints which tells us regarding evolution of universe. We can have knowledge up to some extent regarding evolution of universe using microwave radiation. And in LQG, we know that in low quantum gravity, geometrical observables like area and volume are quantized, and which suggests that at quantum level, our space-time is granular. So we have to measure granularity of space-time if we want to see whether we can have observable consequences of quantum gravity or not. So our space-time is granular at micro scale, but it seems non-granular at macro scale. Let us see first kind of experiment in quantum gravity, that is arrival time of gamma ray burst. In school days, we studied dispersion of light using prism, in which white light is separated or dispersed by prism in 7 colors according to their wavelength. So here, among various colors in white light, which travel with different speed, that we call dispersion in that phenomena. We studied such kind of phenomena in ray optics, considering refraction. If we consider electromagnetic light, which is traveling through granular space-time, which can fill dispersion because of granularity of space-time. And if somehow we can measure this kind of dispersion, we can say that we have experimental signature of loop quantum gravity or any kind of quantum gravity theory. So for visible light, this effect is tiny as its wavelength is of the order of 10 raised to minus 5 centimeter. So we cannot have remarkable or measurable effect for visible light, but we can have measurable effect for gamma rays. Let us see. So in 1960s, US set up satellite to monitor nuclear test ban treaty, which observed gamma rays whose source is celestial in outer space, and it is defined as gamma ray burst. Thereafter, in 2017, in LIGO, scientists observed gravitational waves which is associated with gamma ray burst and came from collision of two neutron stars. So here source is far and lambda is shorter as frequency of gamma rays is more. So chances of detection of granularity of space-time is higher in case of gamma ray burst. So both string theory and loop quantum gravity, which are promising candidate of theory of quantum gravity, are looking for such kind of phenomena, though it is yet to be observed. Here Another strange thing is, I have to confess, though I am a physicist, belong to low quantum gravity community. In low quantum gravity, here strange asymmetrical quantum states are considered, that is left oblique right, left or right. Here to observe such kind of dispersion using Compton Gamma Ray Observatory, which is kind of satellite which observes gamma ray burst. So here, by arrival time of this burst in different frequencies, we can have measurement, or we can have experimental signature of granularity of space-time. But it is yet to be observed because of lack of technology, and as we are talking about Planck energy, which is of the order of 10 raised to 28 electron volt, and we have reached in Large Hadron Collider in the Sun up to 10 raised to 12 electron volt. But somehow in future, physicists will have this effect as its theoretical concepts are clear. And some physicists suggest that as low quantum gravity consider left-right asymmetrical quantum states, it rules out all low quantum gravity theory. But people who are working in low quantum gravity suggest that as we have considered only one state, you cannot say that this will rule out all low quantum gravity. Physicists are looking for quantum states which are corresponding to such kind of measurement in gamma ray burst, which can give us measurement or experimental signature of granularity of space-time, which will tell us that quantum gravity will be successfully measured in experiment or observed in experiment. So this is first way through which we can have observation. Second way is measuring time and distances. Let us see. In 1958, Wigner and Selecker, who are Nobel laureates, wanted to know possible accuracy of clocks. Here, we know that in atomic clock, we consider two mirrors. Between two mirrors, photons are bouncing back and forth, and its accuracy is of the order of 10 raised to minus 18 second. So this is about some basics of atomic clocks. So here light is bouncing between two mirrors, and every hit to a mirror is considered as a tick in such kind of atomic clocks. So here I have shown schematic diagram of photon which is bouncing between these two mirrors back and forth, and each tick will give us 1 second here. Here clock is in the isolated system, so environment will not affect these clocks ideally. Another thing is, in quantum mechanics, if object interacts with the system, it will be spreaded, as we are talking about probabilistic nature of quantum mechanics. So because of constant bombardment of air molecules on mirrors, such kind of mirror will spread and tick becomes less accurate, and that is why it determines inaccuracy of clock, which is inversely proportional to mass, which suggests that the more massive clock we can make, it means the less inaccurate it is. So in principle, physicists suggest that we cannot make any clock as massive as we wish, as it will be converted into black hole. So Checkenji and Hank Van Dam proposed that we cannot make clocks as massive as we wish, as it will be converted into black hole. We know that, as I mentioned here, Planck time is of the order of 10 raised to minus 44 second, and which is best projected to atomic clock, and it has inaccuracy of the order of 10 raised to minus 18 second. So here inaccuracy is proportional to Planck time. So here factor is of the order of 10 raised to 15. By converting inaccuracy in Planck time into inaccuracy in Planck length by multiplying speed of light, we can have this prediction that measuring time and distances. So here it comes in the range of LIGO, and LIGO, which considers high power electromagnetic wave which has more photon, can measure effect of inaccuracy in principle that was proposed by many physicists, but in experiment it is observed that here effect of inaccuracies are averaged out and which was out this possibility. So at present in LIGO we cannot measure this kind of inaccuracy, but physicists are looking for more accurate results in LIGO with more sensitivity, and in future LIGO may have this kind of observation in which inaccuracy in time is converted into inaccuracy in length, and we can have experiment that can give us experimental signature of quantum gravity or quantum gravity. Third proposal is Bell's theorem for temporal order. It considers quantum entanglement. We know that if two or more than two particles are linked or entangled with each other, it means they have shared future, they have shared property, they can communicate with each other with speed greater than speed of light also, and that is why Einstein defined such kind of phenomena as spooky action at a distance. So here such kind of experiments involves a series of inequalities that entangled systems satisfy and non-entangled or classical systems don't satisfy. As we are talking about quantum mechanics, here we have to consider probability and superposition. And to define or describe weirdness of quantum mechanics, we know that at that time Schrodinger came up with its cat's paradox, in which one cat is sit in one closed box and radioactive element is connected with Geiger-Müller counter and also connected with poisonous gas. Here there is a probability of radioactive decay 50%, and because of 50% decay there is a probability of measurement, and that is 50%. If this radioactive element will decay, Geiger-Müller counter will detect it, and at that time cat will die because of poisonous gas. But before measurement we cannot say whether cat is alive or dead, and which is weirdness of quantum mechanics, and that is why it is known as Schrodinger's cat paradox. Before measurement we cannot say reality will behave as either wave or particle, which is known as Copenhagen interpretation. Those who are interested in measurement problem, interpretation of quantum mechanics like Copenhagen interpretation, relational quantum mechanics, hidden variable, many world, and many others, can see videos on this all interpretation in my YouTube channel. I have given lectures in all these interpretations. So group of physicists thereafter proposed that mass in quantum state where position is not well defined, and it leads to entanglement. Here we are considering mass in quantum states, and here position is not well defined as because we are considering probabilistic nature. We don't know whether this particle will behave particle or wave. And here we have to consider causality of general theory of relativity, in which certain processes are responsible for others while others cannot, which are subjected to constancy of speed of light. And two quantum process in which A influences B and B influences A, where final properties of these quantum states can be tested by seeing Bell's inequality that I have defined here. Those who are interested to see what is Bell's inequality, why it is important, can see videos on Bell inequality in my YouTube channel. I have also delivered some lectures on Bell's inequality and also EPR paradox. So in this kind of tabletop experiment, tiny masses are placed in quantum states where position and mass has a probability of being at distant places could provide fuzzy quantum space-time. As we are talking about superposition, similar to wave packet, similar to probabilistic nature, as we have considered in double slit experiment, where we had kind of pattern here because of position and mass, which has probability in quantum states. It can give us fuzzy quantum spacetime, which will again give us another proof of quantum theory of gravity or experimental signature of gravity, quantum gravity. Here, another thing is we cannot measure such kind of fuzziness in quantum spacetime is we are talking about Planck units. As I mentioned, at present, we have reached up to 10 raised to 12 electron volt in Large Hadron Collider, which is located at near Switzerland-France border. And we are talking about Planck energy, which is of the order of 10 raised to 28 electron volt. So there is a large difference. And here another thing is, if we consider wave nature, since wavelength is inversely proportional to energy, in that case, to measure Planck length, we have to supply Planck energy, which is impossible in current technological regime. So, in principle, we can have experimental signature of quantum gravity, but because of lack of technological technology and experimental setup, we cannot measure quantum gravitational effect. But there are certain theoretical results which suggest that in future we can measure quantum gravitational effect, particularly for loop quantum gravity, which tells granularity of space-time at quantum level, at Planck level. So in this present video, we saw various experiment or method through which we can have experimental signature of quantum gravity, or particularly for loop quantum gravity. Thanks for listening. If you like my video, please share and subscribe my YouTube channel. If you have any question regarding these three experiments, that is arrival time of gamma ray burst, measuring time and distances, and Bell theorem for temporal order, you can ask in the comment section. And in the last lecture of this series, we will see some conclusions of this book provided by authors of this book, that is Loop Quantum Gravity for Everyone. And in the last lecture, if you have any question regarding whole book, you can ask in the comment section.